All right, so here's a second problem. Again, we're looking at volumes of solids with known cross sections. So this second problem, instead of looking at cross sections that are squares, we're going to look at a different shape cross section, but we're going to use the same basic premise, the same basic problem, so we can get that good visualization in there. So it says, let R be the region enclosed by the graph of y equals x squared and y equals the square root of x. So same region from before. Region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is a semicircle with a diameter in R. Find the volume of the solid. All right, so first of all, we really want to see what that graph looks like. Again, we know that this is the region R, right in there. And same thing from before, we can keep going back to that acronym. And it says again that we're going to take the cross-sections perpendicular to the x-axis. So we're slicing it like this. That's how we're creating those slices, right? So that's really kind of tell me something about the slices, but we're perpendicular to the x-axis, so just like that. It says, for this solid, the cross-sections are semicircles with a diameter in R, with a diameter in R, so that the part of the circle that we know that's in R, so this part of the circle that we can see in region R is actually a diameter of the semicircle. So again, what does this look like? Well, let's go find out. I'm going to go back to that visualization software. And again, you can kind of see like, hey, there's where our rectangle is. If you watch the first video, it makes a lot of sense. But it says these cross sections are semicircles. So that's what a cross section is going to look like. And we kind of move where that cross section will be. We can move it all around. We can see that when it's in the center, right, it's the largest because it's really got the largest value in R, the largest purple length there. And then when it's right towards the end, that purple length, that length in region R, that diameter is really, really small, and so the circle's not that big. And so again, we can start to see more and more cross sections if we start to change n, right? And so this is what it's going to look like. And the more cross sections we get, we can start to see it's filled in. I don't even know how you describe that, like maybe half of a fat caterpillar. I don't know. We can kind of rotate this around, see it from the top view, right? That's what we would expect to see. There's all those cross sections that I was drawing. Because again, the x-axis is the red axis. We can start to see the height of it, right? Because those are the circles. Start to see it on edge and kind of see that idea of those circles. So this is what the solid looks like. And we know what the shape, oops, sorry, I went too far there. We know what the shape of the cross sections look like. So keep in mind the shape of those cross sections is really just a semicircle. Right? There's our semicircle. So let's go back and let's start to find the volume of this solid. So again, we have our acronym. We know how to find the volume of solids. We really want to look at a picture, rectangle, slice, area, volume, integrate, so Persevi. So let's go ahead and slice this thing. So I'm going to draw my little rectangle because we've got our picture, one of our pictures. It's only one of our pictures. We're going to have lots of pictures. So I've got the picture of the base, that region R. So I know what region R looks like. Whoop. Hoping not use a highlighter there. I know what region R looks like, and that's the base of the solid. It says the cross section is perpendicular to the x-axis. Yes, I cut it so it's meeting at a right angle with the axis. My knife blade would be going perpendicular to the x-axis if I was slicing it up. And it says the cross section is a semicircle, so I want to draw that. So if I were to draw one of these slices, it's not going to be perfect. Not great with writing on a computer screen, sorry. We got this, and it's going to have this tiny little thickness to it, right? And then drawing three-dimensionally here is going to be tough for me. This tiny little thickness to it. That looks like a taco. because of that thickness right there. You can see it. All right, so what do we know about this cross section? Well, we can figure out this height, which is really right here. We did that in the last one, right? So we figured out that we can just use did, distance is difference. We're going to tape the top y value, and we're going to subtract the bottom y value. Okay. And little cheat sheet here. You know, I know that I'm going to have this dx thickness, which really means that I want, and you know, that's that dx thickness right there, which really means that I need to be talking about everything in terms of x. So where is this in terms of x? Where is this in terms of x? And that's why we're, you know, we could have known this because we're taking y value minus y value, distance in the y values. We have to use x values to talk about them. So again, that whole distance right there is going to be the root of x subtract x squared, you know, because those two curves. So the root of x subtract x squared. Right. So I know this about my circle. Now, I want to go back in the acronym. So we've got a picture, rectangle, slice. We even know about the rectangle for this slice. Now I need the area. Well, that's a semicircle. It's a half circle. I know how to find the area of a full circle, right? Area of a full circle is just going to be pi r squared. Pi r squared. And then we're just going to have to take that and chop it in half. No big deal. Maybe I should have wrote that off to the side. But we'll still use it right there, at least for now. So, let's see, what's the radius? Well, the radius is really there out. So I'm going to have to take the root of x, subtract x squared, divided by 2, and that's my radius. What do I need to do with this radius? Well, I need to, this is the radius, I need to square it, and I need to multiply it by pi. Right? So this would be pi r squared, right? Because that orange stuff inside is the radius. Now I'm multiplying, I'm taking the radius, squaring it, multiplying by pi, so I have the full circle. But then I only want half a circle, so I can go ahead and multiply there. Multiply that by 1/2, divide it by 2, whatever you want to see it as. So this is the area of one of those slices. Now we need to make it a volume. That's easy enough. That slice, that taco, just kind of got built backward just a little bit. So it's got this depth of dx, right? Because these half circles all stacked on each other. And then finally, so that's our volume. And then finally, we're going to integrate. And again, keep in mind, we're just adding up the slices. So we're going from slice of height, 0 right there, wherever that was. We keep slicing. Where are we running our knife, right? I'm running my knife, and I run my knife until I get to x equals 1, where those two functions meet. So it's really like, where am I slicing? 0 to 1, those are where my slices are going to be. And this would be the volume of our solid. And so what I didn't do in the last video, because I assumed we can all do this, is I didn't give you the final answer. So if I were to integrate this, and I'm just going to go ahead and do it with a calculator quick, because that's pretty sloppy. I mean, we could try to multiply it out by hand, and honestly, what I probably would do is I'd pull that pi over 2 out front, and then I'd have my integral from 0 to 1, root of x minus x squared all over 2, right? Squared dx. And then what, even multiplying that out, I'm going to realize that there's a 1/2 in here, 1/2. And so I'm going to maybe square that, which would be a quarter, and I could pull that out front. I could make this very much easier, and maybe I'll do that here in a second. But if we actually use our calculator to get this, what we're going to find the value is actually going to be 0.0505 approximately. And if it gave me units, then I would know what units it is. But that looks like that's our volume for this slice, or for this solid. So not very big, but that is our problem. So what I do want to point out, is if I were to go back, and now there's, at this point in time, this is all the volumes of the solid are done. I just want to give you some tips on what I might do if I'm going to integrate this by hand. So keep in mind, I kind of already started us off over here, right? So I'm just going to keep working on this. So what I see is I've got this integral from 0 to 1, and really inside of there I've got 1/2 multiplied by the root of x minus x squared, right? And that whole thing is squared. So I'm just rewriting this inner stuff right here. Just rewriting all of that. And I've still got my pi over 2 out front, right? And what I realize is when I square this stuff inside, that 1/2 is going to get squared also. So really, that's going to become a quarter, and then I'm still going to have this stuff. But only that's squared now, because I already squared the other part. From 0 to 1, and then pi over 2. And really, and there's my dx, I could pull that quarter out front, and because it's just a multiplier, I can either do it inside the integral or outside the integral. And so that's going to become pi over 8, integral from 0 to 1 of root of x, subtract x squared, squared dx. Right. And if I really wanted to keep going, I could multiply that stuff out inside, which really wouldn't be so bad. We would get, if I went ahead and factored or multiplied that out using the area model, or if I foiled it, whatever you want to call it, I'm going to get x subtract 2 root of x times x squared, and then I'm going to have x to the 4th, right? So I'm just really focusing on this piece inside of there. And this looks sloppy to me, because keep in mind what we're trying to do is integrate all this from 0 to 1 dx and pi over 8. But if I think about another way to write root of x, I could really see that that's really x to the 1/2, which is kind of nice. And then, so I could use my exponent rules, and I could say that, that's going to be x minus 2, x to the 5 halves, if I can write 5 there, plus x to the 4th. I don't know why that became really weird down there, but yeah, there we go. Dx, right? So I still need my dx at the end there. So dx, I'm going to take the integral from 0 to 1. I still need to multiply my pi over 8 out front. And now we can see that we could integrate this by hand if we wanted to. It would be much easier. And so I'd encourage you to go ahead and try that. Make sure you get the same thing that the calculator gave you. That way we're just practicing our integration by hand techniques too, which is really important at this point. So hopefully this video helped. Good luck. I'm going to post some homework. Take care of yourselves. Make sure we're studying.